yield lines special cases. And this video deals with circular slabs loaded by a point load on any place on the slab. So let's look at the circular slab simply supported on the edges with a radius of r, and there is a point load somewhere on the slab at distance a of the center of the slab. We will use the method of yield lines, and in more detail we will use the method of attracting yield lines. Because we have a point load in somewhere on the slab, the yield lines will be attracted by this point load. We also know that the axes of rotation are on the edges of the slab. So from a point on the edge of the slab, we will draw a yield line attracted by the point load P. In fact, there are several yield lines, but there are in fact infinite amount of yield lines, because we draw for declarative sum of them. Now let's look at those yield lines. This is the point where the standard load is, and we have to calculate, in fact, the distance to the rotation axis from the point load to the rotation. We need those distances to calculate the mean angle of deflection. So to do so, we will use some coordinates. So P is on a distance A of the center, and we have R. And we use a coordinate system Y, X, like mentioned here. So we take now a point on the circumference, X1 and Y1. And now we know that this point, or this, let's say this straight line here, it's a straight line through the point X1 and Y1. It has an angle or a a slope. It has a slope of the tangents of alpha. I call it the MT, or the MT, the slope. And the straight line must go through the point minus A0, which is the point or the position where the external load is applied to. So we need just the equation of a straight line with a known slope through a certain point on the circumference. So this line, the equation of this line is then, of course, y equals mt times x plus a. And now we are interested in the distance between this point P and the point on the circumference of the circle. And this distance z is equal, of course, to the square root of x1 plus a squared plus y1 squared. We see that z is a function of r, of course, a function of a, the distance where the point load is, and a function of alpha, the corner. So now we can have we can calculate all the distances with this formula. But first we need x1 in function of r, a, and alpha, and y1 in function of r, a, alpha. We got those two equations. This is for the circle, and this is for the straight line. So out of those two, we find x1 and y1. This it has not a closed formulation. It is for certain regions of the slab you have to take care of the sign of the contribution to x1 and y1, but I've plotted it on diagram when alpha in radians from 0 to 2 pi. You see, for instance, for x1, it follows this line, And for y1, it goes like that. So for each sector of the slab, you have in fact another formula for x1, or you have to correct the formula for each one. So this is getting a very lengthy, non-closed formulation of x1, y1. That's why we keep it like this. And then the distance z is then also a function like we've seen of x1 and y1. So it means now that we can put all distances just depending only on r, a, and alpha. Just to give you an idea of the meaning of zr, a alpha is in fact nothing more than a kind of a mean radius of the slab. And take the integral of z by 0 to 2 pi, then you got the circumference of the slab. The result will be 2pr. And if you calculate the integral of z squared divided by 4 pi, you will have the surface of the slab, which is 4 pi r squared. When you draw it like this is a circle, this is the point P on the distance A. Then you have the different yield lines. So you can see that the circumference of the circle is 2pr. And in fact, it looks like that the ZRA alpha is a kind of a mean distance to the point P. To calculate the work done by the internal forces, we shall first look at the general formula, which is the plastic bending moment M divided by the projection of the yield line on the axis of rotation multiplied by the angle of rotation. But in our case, the angle of rotation is not constant, so it's always varying, and the L is also not constant. So the projected length of the yield line is, of course, R times alpha, with alpha in radians, and theta is equal to the unity displacement delta divided by the distance z function of r, alpha, and a. This is for infinite decimal small elements. So to calculate d, we need to take the integral from 0 to 2 pi of this substituted by those, and you arrive at this integral. Just to give you an idea how z is varying from 0 to 2 pi, that's alpha, you will see that for alpha equals to pi, the distance z is here 0.5. It's on it's a curve for r is 1 and a is RO over 2 or 0.5. And this is a function of the angle. In this formula, we call this integral h a function hr and a. Alpha is gone because of the integration. The function h for radius of a unity length of 1 and a distance a, the point of this distance a from the center of the slab, then you still see it is like this. When the point load is in the center, this is a small number. So a small d means a large bending moment. And it approaches infinity when the load is on the edge of the slab. So we know that this is not loud, or it's a silly result. When you have a point load on the edge of the slab, of course, there is no bending moment in the slab. So we know that this region is not very realistic. Just when the point load is very close to the slab, or the forces will go directly to the edge, or the yield lines will be different. Also, the angles of rotation will be too big to apply all those systems. So that's why we stay away from the edge because those results are not very accurate. And to give you a visual impression, this is the position of the point load. These are the yield lines. And you see now for Z equal for this function Z, this is a drawing made for A is equal to 0.5, so it's half the radius. And you will see now that for alpha equals to pi, so it means from there you turn around until here, this is the smallest distance, it's this one. And when you start here, when alpha is defined counterclockwise, when you have this side, then this is the biggest value, and you turn around and you arrive again at the biggest value. That's what this means. So conclusion, the work done by the internal forces is a function of m, of course, the plastic bending moment, and h, a function of r and a. We go now to calculating the work done by the external force. This is very simple. It's P times delta, and the force P times delta. We now also have the internal work, the internal of the work done by the internal forces. We got that too. We know that this is an integral. You cannot put this in a closed formula, so we keep on using those functions. Now, this function HRA is of course equal when you use the unity of length for the circle radius by dividing it by r. So HOA over r is equal to beta, right? And the radius is 1. So now we call this function is just a function of beta because we are working with a unity of radius of circle. Then for E equals D, we can calculate the bending moment, and then the bending moment is of course P divided by H, function of R and A, or make it easier, make it without dimensions. So it will be P divided by H M beta. And HM, when you make a graph of it, you see on the x-axis is beta, so it's from 0, that's the load in the center of the slab. 0.5, it means is the load at 0.5 of at mid section of the radius of the slab. So I've calculated those integrals for different points, and then I've fitted it into a curve, fitted it into a polygonal, and the equation for HM is then equal to this. This means also beta is A over R, and beta could be between 0 and 0.6 because when this curve is approaching infinity and does not obey this fitted curve. So that's why to have a certain range of confidence, I limited beta to 0 to 0.6. So the bending moment can now be directed directly by P divided by this formulation. So as a summary, we can say that for beta equals A over R, on the x-axis is beta. And then you can plot this bending moment, plastic bending moment, as a function of beta. This is plotted for a value of external load equal to 100 kilonewtons. And you will see this is the deflection. So the equation of the bending moment we have seen is equal to that. And we know beta must be between 0 and 0.6. And just to give you an idea, when beta is 0, of course, you have a point load in the center. When beta is 0.6, you see here the very short yield lines. So it means that the slope of the angle or the angle of rotation of those yield lines are getting too big to give you an accurate result. And for instance, for beta equals 0.9, this is not a realistic yield line system, because this load will in practice always go directly to the support instead of to the other side. So for b equals 1, of course, this is not defined. The function is not defined because there is no load on the slab. And beta must be bigger than 0.6, otherwise you have a non-realistic yield line. So this is the summary. When you have a slab, circular slab, simply supported on the edges with a point load anywhere on the slab on a distance a from the center, then the maximum bending moment is the load P divided by a function hm over beta, with beta equal to a over r, and beta is limited between 0 and 0.6. And this is then the graph of the function beta.